So we're gonna let the set be the non-negative integers. So I wish I could just call them natural numbers. There's this controversy. Binary operation is going to be minimum, which I'll just write min. So for instance, what is min of, and 0 is in this set. And I want you to look at this and ask, is it commutative? Associative can be a little bit hard. So if you want to try to tackle that one, feel free. I'm not going to ask you for a proof. I'm just going to ask you to look at it. But then I want us to know, is there an identity element? And then if there is an identity element, are there inverses? And then let's look at the same thing, but let's take the set of non-negative integers and let's ask about the binary operation of maximum. Let's look at the maximum. Now the max of 2 and 5 is 5. Ask the same questions about these properties of a binary operation. Commutative, associative is again hard. Does it have an identity and does it have inverse? We've been talking about the properties that the integers do have and about the binary operations of addition and multiplication. We've actually talked about these two properties before, and so we're trying to see whether these properties extend to other binary operations. So we're looking at the binary operation of minimum on the non-negative integers and maximum on the non-negative integers. As we do this more, I'll give you more time to think about it. And I'll also kind of have higher expectations about your reasoning. Is it commutative? Is minimum commutative on the non-negative integers? Why? Yeah, that's the right idea. So the smaller value doesn't depend which one is written. So it's the smaller number is smaller number. And that's true whether smaller number comes first or not. So minimum doesn't depend on the order. That's what makes it commutative. Is it associative? Because in the end of the day, you get the smallest of the three numbers, regardless of how things shake out. Give a formal proof of this. Suppose I had this special number Q is the identity element. I'm going to assume that one exists. This would have to mean that min P Q equals P for all P. So then we would have PQ equals P for all P, and we would have min QP. That's the definition of an identity element. If this is the identity element, when I do the operation with another element, I got to get the other element back. But can you give me something where I won't get P? What happens? Look at Q plus 1. Consider Q plus 1. Min of Q plus 1 equal to what? What should it be if this were an identity element? It should be Q plus 1, because identity elements are supposed to let things pass through. But I found something where this supposed identity element doesn't let things pass through, so it's an impossible. Q is actually not an identity element, and this is a problem, as we said it was. If we wanted to give a very formal proof. Now, what is this trying to capture? This is capturing the idea that there's always a number that you're not going to be able to let pass through. So because we don't have identity elements, we definitely don't have inverse elements, because you can't, doesn't even make sense to talk about inverse elements without having an identity. What about maximum? Is it commutative? Yes. Okay. Is it associative? Yes. You can steal the same structure of a proof as works for minimum. What about, does it have an identity element? How many of you vote yes? How many of you vote no? How many of you just want to stage a takeover? Not the mind. What's the identity element? 0. All right, let's look at max. So remember, these are non-negative integers. So let x be, I wish I had a symbol for this. It'd be awesome, wouldn't it, if I could just write in the non-negative integers, but alas, I cannot. Too much controversy. Let x be a non-negative integer. What's max of x and 0? It's x, right? Because no matter what x is, it's at least as big as 0. And what's max of 0 and x? And this is exactly what you want in an identity element, right? You want it to let the other element through. So in this case, thus is the identity element for max on the non-negative divided. Now, if I switch this to just be the integers, there would no longer be an identity. It's dependent on there being someplace that you stop. What about an inverse? Do these in general have inverse elements? No, why not? If this such a thing existed, Like if zero had an inverse, if zero had an inverse with respect to max, I should be able to answer this question. The max of 2 and what is equal to 0? And you can't find anything. Because either it's bigger than 2, in which case you get the other number, or if it's 1 or 0, you get 2. So you can't solve this equation. So 2 doesn't have an inverse element in it with respect to max. And this actually doesn't get fixed if you give negative numbers. If you're dealing with integers with no weight. So those are some properties that things can have. And we've seen 2. So I'll give you some more practice with that. But let's just remind ourselves that multiplication is also a binary operator. There are only 2 integers with multiplicative inverses, 1 and negative.